All right, physical computing. Just do it this way. All right, when you talk about physical computing, basically, most basic, involves some hardware, some software, okay, and then sensors reading the microcontroller, reading the inputs from the environment, from sensors, and does some processing and use it to control some output devices or displays. So those be the actuators. So examples, you've got robotics, you've got the IoT devices, you've got the wearable electronics or wearable tech, home automation, environmental monitoring. So the diagram here on the right just shows you the different parts, different subsystems, and uh, basically interacts with the systems in the real world. Okay, and why does physical computing matter? Because basically, if you look around you world today, everything is controlled by some kind of a digital device. So it bridges the gap between the digital and physical world, allows the from educational standpoint, allows the students to have a lot of hands-on experiential learning, and also prepare students for STEM careers and also STEAM careers because it's also this digital fabrication has also gone into the arts and craft area. All right, so benefits of the physical computing. Okay, I split it into different grades of students, like elementary students. Got things like you can use it to introduce basic concepts like the programming concept, sequencing, the cause and effect. Okay, you do something, then causes a change in something else. Can use it to explore the properties of materials. So they generally for the younger students, they have simple things like the makey, where minimal programming required. They can just hook up the devices. They can do programming using a sort of a early the version of Scratch that's meant more for the younger kids, like Scratch Junior. There's the total base kind of device like the B-boards and so on. So you can use it to create interactive storybooks. You can program a simple robot movement. Right. So for the upper elementary, you can build the foundational skills in programming, in electronics. So you can still use the Makey to do coding as well. Can move on to the microbit. One of the nice things about the microbit system like this is that it's got a lot of the sensors, actuators all built into the board. So it's an all-in-one platform, and there's a whole lot of reference materials, teaching resources for it. Then Lego, as Ivan mentioned, it's got a platform for that also, based on work done in together with MIT. Uh, okay, so we've got the earlier version of the Redo, then went on to the Mindstorms platform, EV123, then now it's the Lego Spike environment. Of course, you've got the Arduino. These are popular platforms for elementary level, upper elementary. Now, so projects again, wearable electronics, robotics, you can do home automation, environmental modeling, monitoring. Then you can work with sensors, okay, writing your own storybook, but now integrating with the physical device, okay, getting input from the microcontroller and then controlling the action on the storybook, controlling a character on the storybook. Okay, for middle school, here we move on to a higher level of thinking, problem-solving skills, system thinking. So again, kind of microcontrollers that you use to be things like the Arduino, the microbit, perhaps the ESP32, where you bring a bit of IoT concepts, the Pi Pico, together with some of the other digital fabrication technologies. So things like your 3D printing as part of the problem solving, laser cutting even. Okay, so you work with a larger range of the environmental sensors, the automatic, let's say, plant monitoring, watering systems, the more sophisticated enhanced robotics, wider range of sensors. And home automation systems, smart home systems controlled through the internet. And at the high school level, of course, more advanced STEM fields, so things like IoT, especially the wireless Bluetooth technology comes in, you can experiment. Students can experiment with different platforms. So earlier, younger kids, they will do programming, where typically block level. As they get older, they do the scripting, coding. Usually, for us, most of the students start off with the Arduino platform, but increasingly now you find that with the more powerful boards that can support Python on board, okay, we move on to the Python based coding. So together with the we call that this IoT, which brings them on to the Industry 4.0 platform. So you can build your own drones with the escape controller, the automation system. You can use the AI, because even platform like the this ESP32, the NRF, the boards, the micro bit itself actually supports AI based applications on it as well. So at a high school level, they go on into real world type applications. All right, so here, the right part on the right, that's just an example of a IoT-based system where you link it up with an app on the mobile phone and monitoring, controlling devices across the internet or Bluetooth. Okay, so you find that many schools from primary, elementary school, all the way through to the high schools, they are exploring physical computing as a means of a holistic education, the problem-based, it's called problem-solving approach, holistic education. Um, Using physical computing. So I put in examples of schools from around the world. So US, Australia, Brazil, EU, there's a lot, Asia as well. And of course, the once the students get exposed to this, they are encouraged to work with their local communities, call this NGOs, old folks home, industries, companies to support the tackle problems, challenges that faced by the, for instance, the elderly, by the community, and how they can use the uh, the physical computing, the programming, digital fabrication to solve problems in those areas. Right, because there are programs they can implement at a school level, from half day, full day workshop to a boot camp approach, or even to a whole semester long curriculum, depending on how much time you have, how much support you have for doing it. Okay, so there are programs that can run from elementary all the way through to the high school level. So if you are interested, just we can discuss more about kind of program sample things that you can teach. But again, there's a whole lot of resources on that. Okay, the tools and resources, I put in some common platforms. The things like Makey based for the elementary level, then Arduino microbit, ESP32, the pipe because will belong to the uh, high school level. You've got another popular platform is the ESP32 base, but here they use primarily a GUI based environment called UI Flow. That's the M5 stack. All those things that they are a hot link to the resources that you can access to learn more about it, to learn how to program those platforms. Then software programming in block-based programming, whether Scratch or Makecode. Then you've got the Python-based, Arduino-based programming. And Tinkercad Circuit is a simulation environment which allows you to test out the different circuits using a software simulator. All right, to support that, of course, you need to have the access to things like 3D printers, your laser cutters to create the physical device itself, to integrate the mechanical parts and electronics workbench support, these components and stuff like that. Okay, I put in some samples for the simulators. It's quite fun to play with, especially if we are running classrooms you have issues with students, or before students work on the physical device, especially circuits where they need to do the wiring connection, breadboard or jumpers, find that might be a good idea to start them off on the simulator first. So here, I've got the same automatic night light again. Here, there's no programming. It's just a hardwired light-dependent resistor, and as the light intensity falls, the light turns on. So I've linked to the simulation on Tinkercad Circuit. You can try that. This is another one. It's using a potentiometer to control the light intensity. And the way that we do this in this case here, because the output is either a 1 or 0. So either 5 or 0, but you can control the light intensity by using a technique called the PWM, pulse width modulation. By changing the width of the pulse, you can change the light intensity, because essentially you're sending an average voltage to the LED. Of course, where you can put an LED, you can put in a transistor or FET device, or use a relay to turn on a higher higher voltage light source, or even a AC light bulb or appliance. Okay, so you can try that simulation. You can see there's some code behind it that you can explore if you want to see how that is done. And then if I mention the walkway, this is another very popular simulator. The Tinkercad circuit is very good for the at school level. There's a whole lot of teaching resources, lesson plan on it, which I've linked to as well. Walkway is a modern simulator, touches on a lot of the modern microcontrollers. So things like, besides Arduino, you've got the ESP32, the Raspberry Pi Pico device. You've got the STM32. That means these are ARM-based devices which you can simulate. Okay, and you can even write your own sort of circuits to simulate as well. So here, this is linked to another simulation where it monitors the light intensity. Based on light intensity, it varies the intensity of turn on, turn off the light bulb based on the ambient light. Okay, now Arduino, as I said, there's a whole lot of lesson plan, but there's a lot of circuits that's in there already. But unfortunately, the site doesn't have a very good search engine built into the site. So you can look at projects that people have done, and but to look for a specific kind of project, a bit difficult. It's a lot easier to probably use Google and internet search engine, say what Arduino, and then what kind of circuits you are trying to find. And of course, there's a code that goes with it that you can explore as well. What we supports both the Arduino, the C++ language, as well as programming in Python. So that's one added advantage. Okay, what we also supports Wi-Fi actually. If you want to do the real world across Wi-Fi, there's a simulator built in that you can connect to the internet and then connect and control it through your local network. Okay, so that's Walkway simulator. So just to summarize, the physical computing is very good because it allows you to do the multidisciplinary, interdisciplinary, transdisciplinary, disciplinary kind of approach, cross-curricular connections. For science, look at circuits, energy, data collection, coding to solve math problems, interactive sculptures, digital art, and a whole lot of stuff. Right, so social studies, historical inventions, impact on society, technologies impact on society. So there are a lot of benefits to it, and something that we strongly encourage you to explore and apply to use it with your students. All right, for implementation, okay, maker spaces and trying this. Okay, if you're comfortable with it, then just jump right in. If not, then start small, run a small workshop club. Of course, important that the teachers have the right training and support for implementing these programs. If not, then try and partner with local maker spaces or universities, because all the IHLs, the higher education, we typically have maker spaces or fab labs in there. So partner with them and talk to them. They are normally very approachable. And then showcase, okay, science fair projects, showcase your student projects, work with the local community. All right. So physical computing. Just to summarize again. Fosters creativity, problem-solving skills, innovation, prepares students for careers in STEM. Yeah, students will become creators and not just the consumers of the technology and content. Okay, encourages teamwork, the interdisciplinary, transdisciplinary skills, and exposes students to real-world problems and problem solving.